Today we're going to keep working with the Pythagorean theorem. The only difference is we're not going to be looking at just random triangles on the page. Today we're going to look at word problems. And unlike the word problems that we saw when we were dealing with just linear equations, these word problems are going to paint a picture for us. So before we get into the actual problems, let's talk about what you want to do with these. All right, so the first step, after you've read, of course, is you want to try to draw a picture of the situation. So if you're talking about a baseball diamond, if you're talking about a roof, if you're talking about whatever, draw a picture. All right. Second, you need to ID the measurements and where they go. All right, so for example, if you're given a roof situation and you're talking about how tall the roof is or how far over the roof is, or if you've got a baseball diamond, right? Well, baseball diamonds are in the shape of squares. Once you get the picture drawn, you've got to ID where do those measurements go. So are you measuring from home base to first base? Are you measuring the roof line as the actual roof is, or are you measuring from the inside of the house, maybe from the center of the house to the edge of the roof? You need to identify where the measurements go. And then last but not least, plug your measurements into the Pythagorean theorem. Okay, and remember, that's a squared added to b squared is equal to c squared. Okay, and remember that the a and the b are your leg measurements, where c is the hypotenuse. Okay, so be aware. And if we're talking about just a nondescript triangle here, you've got your right angle, that's what a and b help form, and then c is the hypotenuse. Let me erase that. Okay, so let's start with one. So here we go. It says, if the legs of an isosceles right triangle are 15 inches long, approximate the length of the hypotenuse to the nearest tenth of an inch. All right. Well, let's go back, look at our steps. Draw a picture of the situation. Well, let's look at what situation is being described. It says the legs of an isosceles right triangle. So let's think about that. Isosceles. Isosceles means that we have two sides that are the same. And it's a right triangle, we're told. Well, of course, since we're dealing with Pythagorean theorem, pretty much everything's going to have to be right in order for it to work. So that means if I'm dealing with an isosceles triangle, the two sides that have to be the same length are going to have to be these leg measurements, right? Because remember, the hypotenuse is always the longest side. So when I draw this in, there we go. These two sides have to be the same length. Okay, so that's why I put those tick marks there. This has one tick mark, this has one tick mark. That indicates that they're the same size. There's our right angle, so a right isosceles triangle. And it says the legs. So the two places that we marked here, those are the legs, and they are 15 inches. So let's write that in. 15 inches, 15 inches. Looks good. And we have to approximate the length of the hypotenuse. So this side is what we don't know. We'll call it C. And remember, it says approximate because when we use our calculator, we're going to end up with a decimal that we're going to have to round. In this case, we're rounding to the nearest tenth. So we've drawn a picture. We've ID'd the measurements. We've shown where they go. Now we need to plug the measurements into the Pythagorean theorem. Okay. Well, this is A and B, respectively, and it really doesn't matter since they're both 15. This could be B and this could be A. We don't care. So A squared added to B squared is C squared. I'm going to take my two 15s and we'll plug them in for A and B. So 15 squared added to 15 squared is equal to C squared. Well, let's go ahead and simplify this side. So 15 squared is 225. So another 225. 225 added to 225 is 450, and that's equivalent to C squared. Now remember, we don't want C squared. We want just C, just plain old C. What is that hypotenuse? So 450 is not a pretty number to work with, so let's use our calculator, remember we do second. And then in this case, since we've got a square, we'll undo it with a square root. So we'll do second x squared to get that square root, and we'll type in 450. Now notice, we've got 21 decimal, 21, 32, and so on and so forth. We're just going to the 10th position. So here's the 10th spot. It's that 2, and we look one spot behind, the 1. Well, since 1 is less than 5, we're going to round down, so all the rest of this goes to nothing. So we end up with 21.2, or 21 2/10 inches for the length of our hypotenuse. And remember, since we're finding the hypotenuse, this number had better be long than the leg measurements. And since 21 2/10 is longer than 15, we know we've done it right. Pretty simple and straightforward. Let's try another one. In this example, we're told Betty drives her car 160 kilometers to the north and then 70 kilometers west. How far is she from her starting point? Okay, well, let's draw it out. So let's put Betty, I don't know, we'll put her here. And we'll put start. So again, the first thing we're going to do is draw a picture. So if we were going to draw our compass directions, we've got north, typically we put to the top of the page, and then south, and then we've got east, typically to the right, and west, typically to the left. So let's see. It says she drives 160 kilometers north, so let's draw that in. So she drives north, I don't know, we'll call it that far, 160 kilometers, we're told, okay? And notice, I'm going ahead and putting in the measurements because I know since she drove north, it was 160. So we can go ahead and put that in. And then it says she drove west 70 kilometers. So if this is 160, let's draw that 70 just a little bit shorter. There we go. So she drove west 70 kilometers. So since west and north make a 90-degree angle there, we know that that's our angle. How far is she from the starting points? In other words, here's where she starts. Here's where she ended. What we're wanting to know is that distance. In other words, the hypotenuse. So now that we've plugged things in, this is the distance we're trying to find. We're trying to find that C measurement. Let's go ahead and plug everything in. So A squared added to B squared is C squared. A in this case, I'll let A be the 70 side. Again, it could be the 160 if you'd like, but I'm going to put in the 70 there. For the B, we'll put 160 and we'll square that. And that's equal to C squared. Excellent. Well, I know 7 times 7 is 49. And since we've got two 70s, that's 2 zeros. 16 I'm not as familiar with, so let's take a look. 160 squared is 256. That makes sense. 256 and then 2 zeros, so 25,600 is equal to C squared. Well, since we've got that up, let's go ahead and add the 4,900 to it. And that's 30,500 is equal to C squared. And remember, since we've got that power of 2, we'll undo it by taking the square root. So C, our distance from our starting point to the end point, if we take the direct root, is going to be the square root of 30,500. And in this case, it doesn't ask us to round. So I'm going to go ahead and, since we are talking about kilometers, we really don't measure with kilometers anything shorter than 1/10 of a kilometer. So we'll round to the 10th position. If you wanted to round to the nearest whole, you could say 175. Notice that's a 6, so we could round that 4 up. But I'm going to round it to the 10th position. Since that's a 4, we'll round down, so all this goes away. So about 174 6/10 kilometers. Again, if you went ahead and rounded that to 175, I wouldn't necessarily say that you were wrong. But again, in this case, I'm going to round to the 10th position. It just makes sense given the problem. All right. Well, let's try another one. In this case, a baseball diamond is a square, which we know that. And again, this is just another point of order here. Most of us, when we think of square, we think of something like that, okay, with it oriented with this kind of level with our field of view. If I take that square, however, oh goodness, the telephone, let me get it for a message. Sorry about that. Phone keeps ringing. I can't answer it fast enough. So take a look. If we take a square and turn it, a lot of times people refer to this as a diamond, hence the name baseball diamond, but it's still just a square. All right, so keep that in mind. So a baseball diamond is a square with the side lengths, in this case for this field, of only 54 feet. So that's kind of a small baseball diamond. What is the shortest distance to the nearest 1/10 of a foot between home plate and second base? Well, since we've already got our baseball diamond sort of drawn out here, we'll hold on to it. Now, if you're not a baseball or softball fan, let's kind of clue you in. Home plate is where you bat from. So there it is. And then we run in a counterclockwise fashion. So you run, of course, to first base, to second base, to third base. And then the pitcher's mound is usually right there between first and third, about midway in the infield. So in this case, to the nearest tenth of a foot, what's the distance there between home plate and second base? So we're trying to find that dotted line. So let's say someone at home hits the ball, it goes screaming over the pitcher's head and hits the second baseman and knocks him out, whatever. We're wanting to know how far is that distance. Well, remember, since it's a square, our 90-degree angles will be at the corners. And since it is square, that means the distance from home to first should be the same distance from first to second. And in this case, we're told the side lengths of this particular field, kind of small, but this particular field is only 54 feet on a side. So we'll go ahead and write those in. So again, we drew our picture, okay? Just like we said, we drew the picture. We've ID'd where the measurements need to go. So now that we know that, we can start plugging things into the theorem and seeing what we find. So again, we've got a squared added to b squared is c squared. Remember, a and b are the legs, so in this case, 54 each. And then in this case, c squared is our distance from home plate to second base. So again, if somebody, let's say a gal on the softball team knocks that ball clear over the pitcher's head and hits the second base gal, how far would that ball have traveled? So let's figure it out. And again, I'm not as familiar with 54 squared, so let's figure that out. So 54 squared is 2,916 or 2,916 feet in this case. So 2,916 added to 2,916, and that'll be c squared. I'm going to go ahead and double that, so multiply by 2. Since it's the same, we don't have to add it twice. It saves you button pushes. So 5,832 feet. And remember, we don't want c squared. We want just plain c. So since that's c to the second power, we'll undo it with a square root. Remember, those are the inverse operations there. So I'll take the square root. Now let me show you something handy with your calculator. Instead of having to type all this in, we do second square root if you hit second and then the negative key. Notice how it says above it ANS? That's short for answer. So it'll take our last answer and put it in. So in this case, 76.36, so on and so forth. We're going to the nearest tenth of a foot. So this is a 3. We look over, we've got a 6. That means we need to round up. So this becomes a 4, and everything else goes to 0. So 76.4, or 76 4/10 feet, is our distance for C. Excellent. Not a big deal. So notice, none of these problems are working any different than what we did with the Pythagorean theorem all on its own with just random triangles. The trick now is making sure that we understand, well, what's the real world situation, and can we draw those pictures out, put in our measurements, and work it out? I think I've got one more here. Yep, let's try this. One more here. And then we'll be done. It says, using the Pythagorean theorem, find the area, we'll talk about that, area of an equilateral triangle whose sides measure 6 units. Find the area to the nearest tenth of a square foot. Now let's be real for a minute. Sometimes in the real world, if we're looking at a situation that involves, say, the Pythagorean theorem, sometimes, put that right in there, sometimes finding C is not what it's all about. Sometimes we're going to be using this to find other things. So in this case, we're asked to find the area of the triangle. So let's go back. We're looking at an equilateral triangle, so let's draw that in. See if I can do this. That's not so bad. It's not great, but it's not so bad. So an equilateral triangle, so that means all the sides are the same. And it asks us to find the area. So let's remember what the area formula is. First off, area is measuring how much space is on the inside of a figure. So if I were to take little bitty squares and put those little bitty squares all inside, how many of them would fill it up? So that's when we're talking about area, squared feet or squared inches, not linear, not a distance. Now notice, if we're finding area, the area formula for a triangle is equal to base. So in this case, our base would run from here to here, so that's base, times height. So the height of the triangle would run from here to here and make a perpendicular, so there's h. So base times height, and then we divide by 2. That's the area formula for a triangle. Well, notice, we're told that the side lengths of our triangle are 6 units. So it could be miles, inches, we don't care. So from here to here, the base is equivalent to 6 units. Well, this side would also be 6 units. So let's see if we can work this out. Since our perpendicular comes down and cuts this side in half, that means this short side, notice I made a right triangle, this short side is 3. The hypotenuse, notice there's the long side, is 6. So in this case, in order to help us find the area, we would need the height, which if we're looking at a triangle, here's A, okay, here's B for a leg, and we already know C. So in this case, we'd be finding a leg measurement. In our next video, we'll talk about how do we find a leg measure, and we'll be able to solve problems like this, because so far, all we know how to do is find the hypotenuse if we know the legs. In our next video, we'll look at situations like this where C isn't our ultimate goal. There's other things. This problem not only wants us to find area, but it also will need us to find the leg of this right triangle. And in our next video, we'll talk about how to do that. So again, today, if you've got any questions about Pythagorean theorem word problems, today they'll all deal with just hypotenuse. You'll be good. Remember, draw the situation, identify where your measurements go, plug those measurements in, and you'll be good. And again, today, all we're looking for is hypotenuse. But in our next video, we'll talk about how to find those leg measurements. Have a good day, guys. I'll see you in class.